So today, welcome to the lecture, Math, BEL second semester. We will look at complex numbers. I guess I want to look for the right pen. So, complex numbers. I don't like this one either. Yeah, this is better. So, we've got complex numbers, right? So, we will learn the rectangular form, which is basically A plus J times B. Its geometric meaning we will learn the polar form, which is R sometimes I use I, but I will try to use J. This is the engineering way. And why this is important? Because this is important for frequency. This is important to solve differential equations. This is important for Laplace transform. Basically solve all kinds of engineering problems. We have not enough with real numbers. We need complex numbers. Okay? So we will see why this matters. For some stuff like frequency analysis, differential equations, Laplace transform, to solve these differential equations. Basically, this is the backbone of a lot of things that we will do in the semester and later on. Okay, when you go to the lecture of automatic control, Regelungstechnik in German, you will have this like every day on the plate. So this is basically what we will learn today, if I have time. If not, we will complete it tomorrow. Okay? Of course, you can interrupt me with questions anytime you want. Just shoot, okay? So whenever necessary, just hit me. So if I write the equation x squared plus 1 equals 0, and I ask you a question, can I solve this equation in R, also in the real numbers? No way. It's not possible. Why is not possible? Because in R, in the real numbers, if I say x squared, it's always equal or bigger than 0. right? For every real number, for all real numbers, or for any x belonging to the real numbers. This is true, okay? So as a result, if I add 1 to both sides of this inequality, it keeps being true, right? So this is a contradiction. 2x squared plus 1 equals 0. It's impossible, right? So there is no real number that solves this equation. So we introduce and this is the motivation why we have complex numbers, okay? This very equation. We introduce a new number which has a very specific geometric meaning. I mean, make sure you put this in your, let's say, in your toilet paper. You print this in your toilet paper, and every time you go take a shit, you read it, okay? You need to understand math with geometry. Understand mathematics with pictures, okay? Do not try to, you know, the algebra, it's fine, it's to try to make the whole calculations, but you need to understand the geometry behind math, and this is what I'm going to try to do all the time, okay? To try to explain things with images helps people, helps me at least, understand math better. So this new number is j, okay, such that j squared equals -1, okay? So if we put this j squared into x, let's say if we say j squared plus 1, this is a solution for the equation because j squared is -1 plus 1 equals 0. Okay? So j squared would be, j would be a solution to that equation above. So what is the geometric meaning of j, of this new number that we are looking at? This means j is a solution to x squared plus 1 equals 0. Okay, what is the intuitive, geometric meaning of j squared? This is something that nobody explained to me. I wish they would have. So you're lucky you're getting it explained right now. Imagine I paint the real axis, right? This is the axis with the real numbers. You know, here you have your 0. And then you have here 1, right? Simple line putting all the numbers in a row, negative, positive, whatever number you want, you can paint there, real. Okay, now we multiply this number 1, this arrow going from 0 to 1, right? We multiply this number 1 times j. What happens? This is what happens. It takes us out of the real numbers and turns this arrow, and this is, as I said, an intuitive, okay? It's something that you need to internalize, like your intuition. Like when you say, oh, apples are tasty, you cannot explain why apples are tasty yet. Of course, you could try to make a chemical analysis of the apple and try to find out why you find apples tasty. This is an intuition, like when you like a girl or a boy, okay? You don't know why first, you just like it, okay? So this is an intuition. And this is all we are doing right now. So we are turning this arrow 90 degrees to the left. So if you multiply 1 times j, what you're getting is a vector looking 90 degrees up. If you do multiply 1 times j, what you get is j squared, right? J times j is j squared. So what happens? Somebody tell me what happens. Another 90 degrees, what will happen? What? Louder. You get -1, -1. So we're turning again 90 degrees. What we're getting is j squared is -1. This is the intuitive way to understand j. Okay? Whenever you multiply something times j, you're turning that 90 degrees to the left. Okay? This is an intuition. It's something that, of course, we will see now with algebra, but you need to internalize. Any questions so far? No questions? The more you ask, the more you get, okay? So this is not a barrier, this is not like a tough professor student, so just ask and you get, okay? So a complex number is a number of the form z equal a plus j times b. I'll write it better, I'll write it here. Z is complex, and z equals a plus j times b. A and b are real numbers. Okay? So this is the format of a complex number. We say that A is the real part of Z. B, or we write it like, let's say, real of Z. And Z is the imaginary part of Z. Like imaginary, not because it's something that is unreal, or it's just the way people have given it to it. So, important disclaimer, every real number is a complex number with b equals 0. Okay? This is just a disclaimer, but it's important that you know that the real numbers exist within the complex numbers. So we can write real is inside, is comprehended by the complex. Okay? So when we paint the whole intuition of this complex number in the board, we say here we have our real axis. Here we have our imaginary axis, which is 90 degrees up, and then we say our complex number Z is something like this is Z. It has a real component and it has an imaginary component. Are we cool?
I have one question. Why do you put the J before the B as opposed to after? Is there any reason?
Doesn't matter. It's just nomenclature. You can put the J before the B or after the B. It's just if you multiply 2 times 3, it's the same as if you multiply 3 times 2. It's commutative, so doesn't really matter. It is not a big deal. It's just my way, okay? But you can do it other way around. Yeah, so now what happens if we take this Z, which is A plus J times B, and we multiply this guy times J. What happens now? So what would happen if I say, what is Z times J? Well, this is A plus J times B times J, okay? If we do this, is A times J plus J squared times B, but J squared is what? Minus 1. So this is minus B plus J times A. What has happened? what has happened here is that we are turning this guy upside down. Our complex number is going to be a different one. Okay, so it's going to be, on the real side, it's going to be minus b. On the complex side is going to be a. Okay, and I don't know, this is, let me do it so that it works. So the solution is going to be a new vector turned (90 degrees) to the left. Okay? This is Z times J. Good. This is an example. Yeah.
A small question.
Yeah.
It might be a silly question, but I'm not sure. Isn't, if B is on the y-axis, why is it not flipped on the other y-axis?
Well, if B is positive, B is positive, right? So we take minus B, okay, and it's on the negative. I guess I should put here minus B.
I just meant, why was it not on the y-axis?
Because here, this is the real part. This is the real part, and this is the imaginary part. The real part is minus B, the imaginary part is A. Okay?
Right.
Whatever is multiplying J is imaginary, whatever is not multiplying J is the real part. So another example. Now imagine we have Z1 equals A plus J times B, and Z2 equal say Z plus JD, and A, B, C, and D are real. Okay? We have two complex numbers. Two vectors. So we have equality. A plus J times B equals Z plus J times D. If and only if, this is what this symbol means, okay? If and only if. It's also written IFF, if and only if. A equals C and B equal D. Okay? This is the equality. Meaning that two vectors are only equal if the real part is the same as the other and if the imaginary part is the same as the other. Then addition. A plus J times B plus C plus J times D equals A plus C plus J B plus D. This comes from the very geometric meaning of the whole thing. Let me do a little drawing here. Super simple. If we have one vector, let's say here, Z1 with A and B, and we have another vector here with Z2 with C and D, okay? The addition of these vectors is just adding up the components. The way to do it is putting two parallels and at the end of each build a parallelogram. So the vector resulting is this, okay? All right, I mean, this is adding vectors. Probably you learned this when you were like 12 or 13. This is just another way to explain it. As I said, we start with baby steps. Later on, we'll get hardcore. Okay, addition of complex numbers. Like adding vectors. So then subtraction is the same, multiplication. So we have a Z1 equal A plus J times B, Z2 equals C plus J times D. What does it mean to say we have Z1 times Z2? This means we are multiplying these two things. So this is A times C plus Mahlzeit. J square B times D plus J multiplying B times C plus A times D. Okay, so basically what we've got here is this number A times C minus B times D, because J square is minus 1, plus J B times C plus A times D. Yeah.
The meeting gonna end.
What?
The meeting gonna end, so the notification on the screen.
Oh yeah. Yeah, if nobody joins the lecture,
Yeah.
then it tries to switch me off. So it would be nice if you are on time to the lecture. Yeah. If you're not on time, just try not to make disturbance for the rest. You did, yeah. At least to me. So, we've got that result. This also has a geometric meaning that we will see later on. So, example. One plus 2 times j plus 3 minus j equals 1 plus 3 plus 2 minus 1 times j equals 4 plus j. Okay? This is just adding, subtracting is the same. What if we say 1 plus 2 times g times 3 minus j? This equals 3 minus j plus 6j plus 2. So it's equal 5 plus 5j. All right. Is this clear? So make sure you put your phones away. A complex number z equals a plus j times b can be represented by the point AB in the complex plane. Okay, so the complex plane is what we just saw intuitively. Real and imaginary. So this is the point AB. And the fact of the matter is that talking about vectors in an orthogonal basis is the same as talking about complex numbers. Okay. So the module of z is written like this, equals root square of a square plus b square. This is Pythagoras. You know Pythagoras? It's something like, I mean, you have to know Pythagoras, otherwise, I don't know what the fuck you're doing here. But in case you don't know Pythagoras, this is A, this is B, this is Z, okay? So, what I'm trying to say is deeper. We are assuming that the plane is plane, that we can measure a distance with a line. Imagine you are living in a curvy world. Okay? We smoked a joint together, the joint of friendship, and all of a sudden things get tricky. And the world between us is not straight, it's curvy. Okay? So the straight line would not be the shortest path between you and me. If you look at the Earth, it would be like the geodesic, okay? That's what it's called in geometry. The shortest path between A and B is the geodesic, following the surface in which you can move. So the implication is that we are assuming that we have an Euclidean distance between A and B, which is the shortest path. The geodesic in our complex plane is a line. And this is a big assumption. Of course, we are taking that and nobody explains, and you think that it's always like that. But no, it's not always like that. In fact, when you are in logistics business, as you will be some point, that's why you're studying BEL, right? BEL is business, engineering, logistics. It's almost never Euclidean. When you have a network of IoT devices running around your factory, a network is not Euclidean. You cannot measure a distance between two nodes of a network the same way we are doing here. So the fact of the matter is that reality, when you explain reality with math, is almost never Euclidean. I'm just trying to make this point because later on we will assume a lot of things, but without having the assumptions clear, you will not understand the deepest meaning of it. Okay? So right now we are saying we can measure a distance, but this means we are taking for granted that the world is flat. This complex plane is flat. It's like a paper. Okay? No joints, no smoking, no fluffy, no curves. Okay? Just straight lines. Good. I mean, I'm sorry, I'm trying to explain it so that it's kind of funny, interesting. It's just, I know it's math, it's boring, but I'm just trying to make it a little bit more interesting. So this is the module. So the module is actually the distance between 2 points. So if this is Z, this is the origin, this is our point AB, okay? So the module is just the distance between the two. Good, probably not new to you, but make sure we are assuming here that the world is flat. Yeah.
Just to clear things out, is the module, because I've never heard the term module, is it just displacement? Is module displacement?
The module is the distance, is the length of this vector.
Yeah, but because of displacement, there's the measurement between point A and B.
Yeah.
It might be displacement in certain engineering problems.
All right, but in this one it's
This one is just the distance, okay? It's the length of the vector. At some point, if we are trying to describe a movement, then would be displacement.
So if I would give a definition for module, the truth is this.
Later on, it might be meters, so it's displacement. But if it's, I don't know, if we are describing a dynamic problem, then it's not displacement anymore, okay? So it depends on the engineering problem that we solve. So the complex conjugate of Z is Z with a line A minus JB. Okay, and the geometric meaning of it, always try to explain math with drawings. Always, always, always. It will give you superpowers, okay? Really, if you explain math with drawings, it will give you super understanding powers. So try to do it. This is A, this is Z, okay? A plus JB. What happens if we turn B to minus B? But we keep A. The point turns the mirror on the real axis, okay? This is the complex conjugate. Just mirror. I am going to offer you the possibility to download this PDF, so you don't need to be making pictures all the time, okay? So you can download this PDF, it's for free. It's
for myself now.
for right now, okay. So there you go. Once you jump into the habit of describing math with images, it will become easy. You can solve a lot of problems just drawing, okay? So what happens if we multiply Z times Z conjugate? Well, it happens that following thing. This is going to be A squared minus JAB plus JBA minus J squared B squared. Okay, so if we copy A squared, this cancels. J squared is minus 1, so minus 1 times minus 1 becomes 1, right? So this is A squared plus B squared, which is going to be the module squared. Okay, and this is super important shit. Okay, so if we say Z times Z module conjugate, it equals Z module square. Good. So the complex conjugate will help us divide complex numbers, will help us in a lot of things, so important concept. As we will see in a minute. So the division, we have seen adding, multiplication, now we need division, okay? the division of two complex numbers, let's say z1 divided by z2 equal a times jb plus d divided by c plus jd, is kind of tricky. We want to make, the strategy is transform the denominator, the one below, yeah, I'm just talking to God or Allah, or to help me. Nominator is up, denominator is down. You can also write it on your toilet paper,
Like the dominator is
so you never forget. Okay? Denominator becomes real. That's our strategy. Z1 divided by Z2 equals A plus J times B divided by C plus J times D times. In order to make it real, what do? We multiply that by complex conjugate. Okay? So up and down, numerator, denominator. We multiply by the complex conjugate of the denominator. So the whole thing becomes A times C plus or minus A times C plus B times D, right? Plus J multiplying B times C minus A times D. And below, as we saw, we get Z squared plus D squared. Okay, so this is correct. A times C, and then J squared is minus B plus BD. Yeah, it's correct. BC minus AD. Yeah, okay. So that's the way to divide. This is the division. We can make an example with real numbers if you care. Let's say we want to divide 2 plus 3 times G divided by 1 minus J. Okay? So we say this is 2 plus 3 times J times 1 plus J, complex conjugate, divided by 1 square plus 1 square. This is going to be 2 minus 3 minus 1 and then 3 plus 2 is going to be 5J divided by 2. All right? You cool? So now we talk, this is about the polar form. So now we talk about the polar form. Still have 20 minutes. Polar form is best for multiplication. So space for the multiplication, division, and powers. So the polar form is z, imagine z is a plus j times b, is not 0, okay? Let r be the module, so root of a square plus b square. And let theta be, this is a Greek, be the angle between positive real axis, and this is super important, is the angle between the positive real axis, not the negative real axis, or not some other fuck, okay? I say what I say, not what I don't say. This is important, okay? So make sure you read and understand what is there, because some other people will start, oh no, I measured it from the negative real axis. No, then it's wrong, okay? There is only two ways here, it's just black or white, right or wrong, okay? The positive real axis and the vector z, okay? So what if we paint this, okay? Let's paint the polar form in a way that is intuitive. So this is the positive real axis. This is the imaginary axis, okay? And we have our little vector here, z, jumping around, okay? It's a very straight, very educated vector, just pointing always the arrow there. Okay, so we have this way to position this point AB, okay? This is equal to AB. What way will this be? Well, we can rotate theta here and go all the way the module from the limit, from the 0, and we will be there, right? If we are here, imagine this is our origin, we expand zeta here, and then we rotate it, we expand the module, and then we rotate theta. This way we will get to that point as well, right? We expand the module and then we rotate. We get to the same point. This is the polar form, nothing else. Instead of saying A and B, which is somehow not very natural for many engineering problems, we just go ahead and say, okay, we are going to understand this by getting out of the origin and rotating. Guess what? Many engineering problems are about rotation. Imagine a motor, imagine some frequency stuff, imagine, a lot of things. All right? So, zeta, z, or however you want to call it, is r times cosinus of theta plus j times r sinus of theta. Okay. There is one guy, some German Klugscheißer, as they say here, who said, whose name was Euler. Maybe you've heard of him, maybe not. Very important guy. Said this is about E, J, theta. What?
Is E related to exponential?
Yeah, A is the exponential. This is a Euler way to write it, okay? So theta angles are not unique. Very important for an engineer as well, because if we turn theta 2 times pi one way around 360, we end up with the same point. If we turn this vector 360 degrees, we end up where we started. Right? No? If we turn around here, so theta is not unique. All these are solutions of the problem. And this is the basis for frequency analysis later on. Okay? So here sometimes I write with when you need to be cautious, I paint here my warning sign. Some guy telling you, be careful. Sometimes students use theta as the inverse of the tangent B divided by A. That is dangerous. Because it might give you the wrong quadrant. So please always, when I say always, I mean all fucking ways, check the sign of the real part. Because the tangent of this vector and of this vector going to be the same. Always check the real part. If it's positive, it's going to be on this side. If it's negative, it's going to be on the other. Yeah.
Right.
What?
No, sorry.
No. Always check the sign of the real part. Okay? So example, convert to polar form. R is square root of 1 plus minus 1 square. So square root of 2. And theta is tangent inverse of 1 divided by 1, or minus 1 divided by 1. This is going to be pi divided by 4, because the real part is 1. 1 is bigger than 0. Okay? Yep.
So the same verification again.
What?
The same verification again on the screen.
Oh yeah, thank you. Yeah, this will not happen when you're online. So yeah, the exponential form, or the Euler's formula, is E j theta equals cosinus of theta plus j sinus of theta. So the polar form Z is R E I theta. Okay. This is the polar form of the exponential of the complex number. All right. So for engineering, this is one of the most useful formula series in all mathematics. Okay. It turns trigonometric expressions into exponential expressions, and that makes your life so much easier, because the derivative of the exponential is the exponential, and the integration of the exponential is the exponential. So it's super easy. Okay?
So can you repeat that again?
The derivative of the exponential function is the exponential function. So if you turn some complex trigonometric shit, like hyperbolic tangent or something, and you can describe it as exponential, then your life is much easier, because you can derive it, you can solve equations much easier, right? So when you now multiply, add up, or something, if you have two numbers, if you had two complex numbers, R1, E, and you want to multiply them, then Z1 times Z2 becomes like a piece of cake. Right? The division, again, becomes piece of cake. And so on, right? So geometric interpretation multiplying by E equals J theta means rotate by angle theta multiplying by R means scale by factor R. Okay. Questions?